Hi everyone, I'm Li Mingdong from Tsinghua University. I'm going to present our work, Marviq, quality-aware geospatial visualization of range selection queries using materialization. This is a joint work with UC Irvine. Nowadays, we have more and more location-based services like Twitter, Uber, Airbnb, etc. And usually their data volume are very large and growing very fast. Spatial visualizations are very important tools to help users get useful information from their data. There are many different ways to visualize data, for example, the skid plot and heat map. Typically, a visualization system has three tiers: an underlying database, a front end, and a middleware in between. Users can send a visualization request at the front end, and the middleware translates the request into a query and answers into visualization result. The front end plots all the result to users. In our paper, we consider this kind of general form queries. Select coordinate from table where value between V1 and V2. For example, if a user wants to visualize a skid plot of tax pickups between January 1 and April 30, then the corresponding selection condition will be time between these two values. If the dataset is very large, then it may take a long time to execute the cycle, transport data to the front end, and plot all the points. For example, in one of our experiments, to visualize the skid plot of some ranges from a dataset of 1.3 billion records, it took about 20 minutes, and most of the time was spent on retrieving data from the database. Our solution, called Marviq, addressing this problem by dividing the entire data domain into intervals. It can be used in multiple attribute conditions, different visualization types, etc. Here, for simplicity, we take single attribute and skid plot as the example. In our paper, we presented all the generalizations. Suppose this line is time and can be treated as numerical attribute. Marviq first divided it into intervals, for example, by month. Then pre-compute the exact visualization of each interval, which was called EV. For example, the exact visualization of January, February, March, and April. And EV are stored in a structure called MVS. For skid plot, we can just store the coordinate of each point. Then for the previous query, we can use the union of these four EVs as the answer. And this answer is exactly the same as the visualization produced by 4-month data from the base table, but much faster. However, we're dealing with ad hoc queries, so not all of the query ranges were aligned to intervals. For example, one of the query range was from January 15 to April 15, completely covered 2 EVs, and have 2 gaps at the beginning and the end. In this case, to compute the exact visualization of this query, we need to retrieve data in these 2 brown ranges from the base table, and together with these 2 blue EVs from MVS table. Because retrieving the 2 blue EVs were very fast, so the total response time can be greatly reduced. However, retrieving the data in the brown ranges was still too expensive. That's because the base table was usually very large. For example, it took less than 10 milliseconds to retrieve those 2 EVs, but may spend several seconds to retrieve the data in the brown ranges. We propose several techniques to improve this. The first technique is to provide approximate visualizations. For example, the left figure was using data in the whole selection range, and the right figure was using data in February and March. We can see that these two figures are very close, even in zoomed-in region. When providing approximate visualizations, we need to know the quality of them. There are many quality functions can be used. For example, the PSNR, SSIM, MC, GCAD, and etc. And the users may have their own quality functions. Also, we need to know what kind of approximate visualizations is good enough to users. That is the threshold of the quality. We noted it as delta. So the purpose of quality-aware approximate visualization is to compute a visualization with quality no less than the threshold in the given function f. For simplicity, we use the GCAD function here. Suppose we want to use the union of the two blue EVs as the approximate visualization. Apparently, in GCAD, its quality is this. Remember that in the denominator, we need to retrieve the data in brown ranges from the base table, which is very expensive. Instead, we can use the superset of their visualization. That are these two brown EVs. Because these EVs were already computed and can be retrieved quickly. And because the brown EVs are supersets of the visualization of brown ranges. So the quality is greater or equal to this. And it should be no less than the delta. In our paper, we identified some properties that quality functions should have. Any function that satisfies these properties can be used in Marviq. If the quality is larger than delta, then we can simply return the union of these two EVs. Otherwise, we need to retrieve the records in brown ranges. We presented another technique to further reduce data volume to be retrieved from the brown ranges. We achieved this by extending MVS to MVS+. We introduced two-level granularity intervals, the parent interval and the child interval. We first divided the data domain into parent intervals by month and pre-compute EVs for them. Then divide each parent interval into several child intervals, for example, by week. For each child interval, we pre-compute and store low-resolution visualizations for them, called LV. LV is computed from the corresponding EV. Each pixel of LV represents several pixels of EV. Then we can use EV plus LV to compute the approximation quality. The details of quality estimation in MVS+ can be found in our paper. As a result, because we have more information about the distribution included inside the parent intervals, so we can reduce the amount of data retrieved from the brown ranges. For example, we can only retrieve a subset of them and compute an approximate visualization. In our paper, we presented many other results, including the generalization of multiple attribute conditions, heat map, and many other quality functions, and also the support of zoom-in, zoom-out operations. We used the three data sets in our experiments, the Foursquare, tweet, and New York text pickup data, and used PostgreSQL as the underlying database, which was running on a single server. We first did a Euro study to verify the idea of Marviq. In the Euro study, we compared Marviq with sample seq and VAS. and we gathered 36 participants and generated more than 300 images. The results show that Marviq can produce higher quality results than SIGMOD and VAS. And for the same quality threshold, Marviq has lower storage and response time. This is the offline construction time of Marviq of the New York taxi data. The x-axis is the interval length. We can see that it only took about 40 minutes to pre-compute all the EVs. Over 99% of the time was spent on retrieving the data from database, so the time was very stable due to different parameters. And the storage size is only about 1 to 2 gigabytes due to different resolutions, which was less than 1% of the original data set. This figure shows the response time of computing the exact scatter plot of New York taxi data. And the x-axis is the query range length, which ranges from 1 to 5 intervals, and each interval is 1 day. The response time of Marviq, including the time of accessing base table and MVS table, and time of accessing the base table is dominant. So the total response time of Marviq was very stable, and it can compute the exact scatter plots in less than a half second. And this time can be further reduced when providing approximate visualizations. In conclusion, our work focusing on the problem of spatial visualization of the large data set using SQL queries with ad hoc select conditions on numerical attributes. And our solution is dividing the data domain into intervals and pre-computes and stores a visualization for each interval. With these pre-computed results, it can provide exact visualization or approximate visualization with quality guarantee. Thank you.